Hello, can you hear me?
Yes, sir.
Yes, sir.
And can you see the slides?
Yes, sir.
Okay, great. So, welcome to the course of Nanoscale Modeling and Simulation. And today I would make it, pretty introductory, pretty general. Gradually, we will go inside the course. The purpose of the course I would explain today. There are three terms. One is nanoscale, another is modeling, and the third one is simulation. Let's see how we could play with those, three words and where we could reach. So, to start with, what is nanotechnology? I'm sure you have listened to this definition from many people. There are many definitions also, but according to the National Nanotechnology Initiative, it calls nanotechnology only if it involves all of the following. Which ones? One, research and technology development at the atomic, molecular, or macromolecular levels in the length scale of approximately 1 to 100 nanometer range. If the dealing of a matter, like if we do research, if we do technology development, it should be within 1 to 100 nanometer range. Creating and using structures, devices, and systems that have novel properties and function because of their small or intermediate size. It is not because of the general property, it is because the change of property due to the change of size, due to the transformation from the macro scale to the nanoscale. And last but not the least, ability to control or manipulate on the atomic scale. From bigger one, we keep it to lowering their size and ultimately coming to the level where it is on the atomic scale. So, where we start, it could be easily understood that it is in a bigger way about size. So, how we understand size? That's one of the key idea pushing us towards nano dimension. So, if we try to understand size, look at this beautiful tree, and when we look at, we generally get to visualize materials here in the level of 1 meter. But if we go and focus on a leaf, we are actually going down from 1 meter to 10 centimeter. If from there, if you see on the leaf, there is a insect, there is a bee, and when we focus more, we come to the measurement of 1 centimeter. Now we are looking at the eye and we come to the level of 100 micrometer. Again, going to more focused, we go into each of the unit in the eye and we come to the size level of 10 micrometer. Again, now we focus on each of the units connection and we arrive at 1 micrometer. Focusing further, we focus on the thing which is in the juncture, in the connection, and now we arrive at 100 nanometer. We go further, we go to their DNA, we are arriving at 10 nanometer. We are going to the atomic level, we come to 1 nanometer. So, size matters. We have to understand size, and understanding size and changing the properties around the change of size, that's what we are going to study. If you look at this guy, if you compare with this guy, is big, but it is not only the bigger size which matters, it is also how it could hold a weapon and attack the other one that matters. So it is not just how big you are, it is what you can do with it, how you could utilize the size you have. That's what matters. So, how small is nano? We are talking about nanotechnology. So, we have to understand how small is nano. And if we start from a tennis ball, we have to go gradually from tennis ball to period to cancer cell to bacteria to virus to antibody. When we arrive at virus, we arrive around 100 nanometer, where actually all the nanomachines are restricted. Then we go to antibody, which is around 10 nanometer, glucose, which is 1 nanometer, a droplet of one atom of water is zero point 0.1 nanometer. So, which are nano devices? Nano devices are nanopores, dendrimers, nanotubes, quantum dots, and nanocells. Generally, their size varies between around 5 nanometer to 500 nanometer. We will talk about, we'll see a lot of those variations, their measurements, their possibility to develop complex, and that's what the journey would all about. Also, it's a different representation. How small is nanotechnology? You could see that a small child is about 1 meter high, and that's one in with 9 zeros, that much nanometer. So 10 to the power 9, that much is the difference between 1 meter and 1 nanometer. So, as I told, in our course, which is nanoscale modeling and simulation, we will deal with three things. One is nanoscale, another is modeling, and the third but the last one is simulation. So let's start with nanoscale or nanotechnology, what we are talking about. So nanoscale usually refers to the structures or entities which keeps themselves within the scale applicable to nanotechnology, which we have talked about, usually cited as 1 to 100 nanometer. Nanotechnology is science, engineering, and technology conducted at nanoscale, which is about 1 to 100 nanometer. Nanoscience and nanotechnology are the study and application of extremely small things and can be used across all of the other scientific science fields such as chemistry, biology, physics, material science, and engineering. In a true sense, it is a science which could be considered as an interdisciplinary science. The arrival of nanotechnology is considered as the arrival of new era, and I will try to take different historical perspective to show you how the field arrived and how it continues. But let's start with the guy called Richard Feynman, one of the greatest physicists the world have got. The ideas and concept behind nanoscience and nanotechnology, it started with a talk of Richard Feynman, which called There is Plenty of Room at the Bottom. And the talk was hosted at an American Physical Society meeting at the California Institute of Technology, Caltech, which is known as on December 29, 1959. Think about December 1959, where Richard Feynman described a process in which scientists would be able to manipulate and control individual atoms and molecules. Very interestingly, Richard Feynman and his contributions would be coming in when we proceed with the field, our journey. You will see that the two fields, the dynamics of molecule with the nano machine, how was connected by the work of these stalwart physicists. So keep an eye on Richard Feynman. But Richard Feynman, being the father of nanotechnology, is not the person who actually coined the term nanotechnology. Over a decade later, in his exploration of ultra precision machining, Professor Norio Taniguchi, you could see here, this is Richard Feynman and this is Professor Norio Taniguchi. He coined the term nanotechnology. But it was not until 1981, with the development of the scanning tunneling microscope that could see individual atoms, that modern nanotechnology began. So, people are talking about the concept. Richard Feynman long ago have described about the possibility to manipulate and control the individual atoms and going into different properties of the atom. So that was there, the conceptualization was there, but it started with Norio Taniguchi, who coined the term, but still people were not being able to realize with the advent of higher resolution electron microscope, which I am going to talk about, scanning tunneling microscope, atomic force microscope, they have pushed the world of the field which is now popular as nanotechnology. It is hard to imagine just how small nanotechnology is. As we have seen, 1 nanometer is a billionth of a meter or 10 to the power minus 9 of a meter. And to understand it, you could take examples which will help you to understand. There are 25,400 thousands nanometer in only 1 inch. A sheet of newspaper is about 100,000 nanometer thick. On a comparative scale, if a marble were a nanometer, then 1 meter would be the size of the earth. So those three examples will show you the smallness of nanoscale. Nanoscience and nanotechnology involve the ability to see and control individual atoms and molecules. It is not only to look at, but it is the ability to visualize as well as to manipulate, to control the individual atoms and molecules. Everything on the earth is made up of atom. The food we eat, the clothes we wear, the buildings and houses we live in, and our own bodies. So, the ability to control on the atoms and molecules gives us the enormous capability, the enormous power to control the universe. And that's the beauty of the field called nanotechnology. But as I told, the progress of the field was restricted by the fact that something which is as small as an atom is impossible to see with the naked eye. In fact, it was impossible to see with the microscope, which you see typically in your 10th level, 12th level classes. In science classes, you use them. That is called light microscope. It was also impossible. The microscope needed to see things at the nanoscale were invented in the early 1980s. Once scientists had the right tools, such as I talked about, the scanning tunneling microscope or STM and the atomic force microscope AFM, the age of nanotechnology was born. So this is scanning tunneling microscope, where it's a electron microscope. There is a tunnel, a continuous scanning happen, and it ultimately creates a 3D picture, high resolution. This is atomic force microscopy. Here, this is the substrate, and this is the sensor. It comes, it interact with the substrate, and it could take the image as well as the surface. It get the surface property of the material. So images, initially there are images of organs, there are images of pollen. You might nowadays, we are very much biased. So looking at that, you might think about coronavirus. No, it's not. They are actually pollens. These are cells, red blood cells. So from organ to pollen to cells, there is a journey towards the smaller dimension. And you see here, these are different nanoparticles. You see that all the images were taken at 100 nanometer. You could see the 100 nanometer dimension, and this is 20 nanometer, and you see different nanoparticles. It's even more interesting with the high resolution. It make you able to see atoms. So you, from nanometer, you are looking at angstrom level. So with the journey of capability of taking images in the higher resolution, we get a new field, which is nanotechnology. Because as I talked, nanotechnology deals with the smaller volume, the smaller space, and it is the space we are talking about could not be visualized with normal eye, could not even be visualized with simple light microscope. Only with the use of very, very high resolution electron microscope, it was possible, and the resolution keep increasing. We keep seeing the unseens, and development of the field happen. So this is a very interesting comparison. You could see here, the bigger thing you see is the single human hair, whereas the smaller fibrous things are nanofiber. A human hair in its width is about 100,000 micrometer. When we talk about nanotechnology, we could not spare to talk about nanobiotechnology. Why? Because, very interestingly, at the lowest size, which is the nanoscale size, we see it defines the unit of lot of the biological substances. And that's where research on nanotechnology have a very interesting role in solving the problem of medicine, solving the problem of biotechnology, hence the field nanobiotechnology. If you look at the key dimension in nanometers, DNA double helix has a diameter of about 2 nanometer. A bacterium of the genus Mycoplasma, the smallest one, has a length of 200 nanometer. A red blood cell is 6,000 nanometer in diameter. A human hair, as we already talked about, 800 nanometer in diameter. To put this scale in context, the size of nanometer to a meter is the same as we have already talked about, that of a marble to the size of the earth. So I am repeatedly talking about the size to give you an idea about what we are talking about where the interesting point lies. So small things are different. Nanoscience would be boring if small things were just like big things. If you take a ball and then a marble, make up of the same material of the ball, you don't see the change of the property. So you are not excited to compare between them. They are just different by their size. But if you could reach on the nano level, you see very interesting changes in its intrinsic property. And that's why nanoscience, nanotechnology is so interesting. The color of gold changes with size. When you see 10 million nanometer, you see the normal gold. When you see 10 nanometer, you see different color, different properties. When you see 1 nanometer, it's again different. Graphite, for example, takes on interesting shapes if it is kept from becoming a big solid. Graphite, buckyball, nanotube, different interesting shapes and properties. The goal of nanoscience is to find and understand how physical properties change with size. So now we know that in the journey of nanoscale, there is infinite change. And the correlation of this change comes through the understanding, the finding of how the physical properties change in size. Materials which are reduced to the nanoscale can show different properties compared to what they exhibit on the macro scale. For example, copper, which in general opaque substance, it become transparent. Stable material turn combustible in case of aluminium. Insulators become conductors in case of silicon. Solid turn to liquid at room temperature in case of gold. So nanoparticles tend to be more chemically reactive than their ordinary size counterparts because why? Because they have more surface area. Really? We are going to check. An increase in surface area to volume ratio alters the mechanical, thermal, and catalytic property of materials. So, nanoparticle, we know now that they change their property. But the question is, how they are going to change their properties. They tend to be more chemically reactive than their ordinary size counterparts because they have more surface area. And an increase in surface area to volume ratio alters the mechanical, thermal, and catalytic properties of the material. So let's look at the unique property of nanomaterials. The nanostructure or nanomaterials exhibit properties different from their macro scale counterparts, such as mechanical strength, how hard they are to break, electrical conductivity, how fast electrons flow through them, thermal conductivity, how fast heat flows through them, chemical reactivity, how well or how fast they react with other chemicals, transparency, how well you can see through them, and magnetism, whether or not they are magnetic. And that brings us to the section where we are looking at different nanomaterials. 0D nanomaterial, which are called nanoparticle or nanospheres. Nanoscale lengths are measured in all three dimensions. When in all three dimensions they are able to keep the size within nanometer, then they call nanosphere or nanoparticle or 0D nanomaterial. Nanotubes or nanowires or nanorods. When two dimensions are within nanometer but one is not, then they are called 1D nanomaterials, or they also called nanotube or nanowires or nanorods. When then come to nanoscale thin films or ultra thin films, and nanoscale lengths are measured in one dimension only, other two dimensions are more than nanometer. Then they are called nanoscale thin films or ultra thin films or 2D nanomaterial. Nanocomposite, a material comprised of many nanoscale inclusions such as nanoparticle. If you have 3-4 type of nanoparticle together, they are called nanocomposite. Nanostructure material or 3D material, a material that exhibits a unique structure that can be measured at the nanoscale. Buckyballs, nanoparticle comprised of exactly 60 carbon atoms, though there are other type also which are called buckyballs, forming a network that resembles a soccer ball. That's why it's called buckyball. So why does this happen? Nanostructures, they obey the same fundamental laws of the universe as everything else in the nature obeys. But some things that are negligible at big scale cannot be ignored at small scales. And I have a very interesting example for you for that. So, before going to what I have wrote here, think about you are riding a bike in the road which is going from Roorkee to Delhi. Now, if some camera is focused on you, it could capture your continuous motion. Now, if the road is as you could see it now, broad and big, it would be difficult to keep track of you always, right? So you are running on a bike and a camera is all over. Sometime it is taking you, it is getting you, sometime it is not. But suddenly the process comes into, from these big roads you have to go to a specific place, so you come from this big road to a smaller road. Now this is a very small road, so the camera is now focusing on you, and because it's a small road, you have also higher chance to collide with coming, you know, cars or other vehicles. So when from a broader area, a big scale area, you transfer yourself to a small scale area, your visibility increase, your surface property is more studied, and your property is different. In the big road, you are having much less chance of colliding with others. In the narrow road, your chance of colliding with others enhances, so your property change. Coming back to, forget about that story. Now imagine you are an electron moving through a big copper wire 1 centimeter in diameter. So this is a copper wire. Again, compare with the big highway, and you are an electron traveling. You may never see the boundaries of the wire because you are so small compared to its diameter. So you are electron, you are traveling in a big copper wire, you are never probably going to see the boundaries. But now, instead of big copper wire of 1 centimeter diameter, you are transferred to a smaller copper wire of 1 nanometer in diameter. You are the same electron. Now you bump into the boundaries of the wire often, which affects how you move through the wire. Therefore, the 1 nanometer diameter copper wire exhibit different electrical properties than its macro scale counterpart. So, if you go through, your visibility increase, your surface property increase, and you exhibit different property. Exactly what happened in case of changing dimension from the macro scale to the nanoscale. You have the entire road in macro scale, you go relax, but now you come into the small road, you are constantly watched by the video, and you are bumping here and there. I will try my best to show now the example I have given with theory. So increase in surface to volume ratio. So if you see the box here, which is having each of the 1 meter, the area is 6 into 1 meter square, which is 6 meter square. But the same size box you create taking many small boxes, you see that the area now become doubled. So single box ratio 6 meter square by 1 meter cube equal to 6 meter square by meter cube. Smaller box is 12 meter square by meter cube. Neglected, obviously we are neglecting the space in between. So neglecting spaces between the smaller boxes, the volume of the box on the left and the boxes on the right are same, but the surface area of the smaller boxes added together is much greater than the single box. Same story you could see using a sugar cube. If you take individual sugar cubes, is about 1 centimeter on a side, so each side has an area of 1 centimeter square. Within 6 sides, it has a surface area of 6 centimeters square and a volume of 1 centimeter cube. So the surface area to volume ratio is 6 centimeter square by centimeter cube. Now, if you take 64 such sugar cubes to make a block, they have showing arm value of 4 centimeter on each side and a surface area of 6 into 16 centimeter square or 96 centimeter square and a volume of 4 into 4 into 4 64 centimeter cube. This is a surface area to volume ratio of 1.5 centimeter square by centimeter cube. So if you compute the surface of all 64 individual cubes, you would have 64 into 6 centimeter square or 384 centimeter square or 4 times more surface area with the same total volume. Now comes to, so we understand the surface property, the surface exposure. Now the second property of nanoscale material, which is quantum confinement. In small nanocrystals, the electronic energy levels are not continuous as in the bulk, but their discrete finite density of states because of the confinement of the electronic wave function to the physical dimension of the particle. This phenomena is called quantum confinement, and therefore nanocrystals are also referred to as quantum dots. In any material, substantial variation of fundamental electrical and optical properties with reduced size will be observed within the energy spacing between the electronic level exceeds the thermal energy, which is kT. In addition to that, the nanocrystals possess a high surface area, as we have already talked about, and a large fraction of the atoms in a nanocrystal are on its surface because of its enhanced surface exposure. Since this fraction depends largely on the size of the particle, let's say 30% for a 1 nanometer crystal, 15% for a 10 nanometer crystal, it could give rise to size effect in chemical and physical properties of the nanocrystal. So, how surface to volume ratio works with animals? If you look at the rat or mouse, its larger surface to volume ratio, they are very susceptible to changes in heat. If there is change in heat, they are the mostly affected. Whereas a big animal, let's say a bear, smaller surface to volume ratio, so they are less susceptible to changes in heat. So this is also a theory. So coming to the summary, as I told, I would just go through a journey today. We talked about what is nanotechnology, how nanotechnology was coined and discussed, and how nanotechnology works with its difference than the macro scale, the reduction of size from macro scale to the nanoscale. How the properties of material changes from macro to nanoscale. Also, by this change, it appears to some unique properties, and those unique properties gives or solve a lot of problem, innovate a lot of technologies. That's what we get from the field of nanotechnology. Now, remember I talked about there are three aspects: nanoscale, modeling, and simulation. We started understanding what is nanoscale, how nanoscale is so special, how nanoscale is coming up with unique properties, but at the same time, what we are going to model. If we are understanding it correctly, nanoscale is pushing us to the smallest unit of a substance. So if you are going into the smallest unit, how you are going to design further, how you are going to model further? This is a very interesting question. I want everyone to think about. That's why I repeat the thing. When we start our journey, when we are talking about nanoscale, we know that nanoscale defines the smallest unit of many of the substrate. So if we are achieving at the smallest unit, we are not going to change further, then how we are going to model it? The second question is little more easy. We are going to look at the assembly of nanoparticles, the interaction of nanoparticles with other nanoparticles, with polymers, with biological macromolecules and all. And while doing that, we want to look at their dynamics. So that's what we are going to study in simulation. As I told, nanobiotechnology is taking a very interesting role here because in biology, again, most of the smallest unit of all the macromolecules, organs, and most living and non-living species are in the nano level. So that gives nanotechnology empowered with a very interesting ability to solve a lot of problems in biology. But we have to understand how, and we have to get into how we are going to study them, how we going to know them, and how we are going to involve them in further study. With this, I'll stop my class for today, and I would like to ask the students, as I am asking throughout the class, nanoscale being the smallest scale, the smallest unit, what we mean by modeling nanoscale. So I would love to hear from all of you. Anyone? No? Hello?
Yes, sir. Yes, hi, sir.
Yes. Please. Hello? Hello?
Yes, sir.
Yes.
So
Tell me.
maybe looking onto the organization of the atoms.
First of all, we would have a rule because I don't know all of you and I cannot see all of you. So when you are saying something, tell your name, okay, and then, okay, yeah, please continue.
Sir Rutuja.
Rituja.
So maybe the organization of the atoms and how they are interlinked with each other.
No, explain a little bit like how that could be a modeling. That is already there, na?
So what outcome can we get out of that?
No,
Like
but
how can we project?
when you say modeling, it's not only to check the organization, right? Modeling comes by incorporating something into a designing perspective, a modification, right?
Yeah, sir, like what can we project this organization into?
Explain a little bit, sorry.
So maybe what outcome can we get out of modeling these nanomaterials? Maybe the designing or
No, that's what I'm saying. How you design, how you modify them, how you modulate them. If you consider nanoparticles, you cannot go beyond, right?
yes, sir.
Are you getting the question? Because I always find it very interesting to start this course with this knowledge that what it means by nanoscale modeling. Why even there is a course called nanoscale modeling. Nanoscale तो समझ में आया, मॉडलिंग करना क्या है यहाँ? Others, it's always encouraging, to talk as Rutuja have interacted, especially when we are sitting in a room where we cannot see each other, interact with each other physically. It would be very nice if you talk, and there is nothing wrong or right. What Rituja told, it's a concept, and providing a concept does not mean or does not could not be judged in terms of right or wrong. It's just helpful addition to the idea we are talking about. First of all, thank you, Rutuja, for interacting. And I really hope you guys would interact. I would explain these in the next class, and I would let you all think, and I would be loving you guys, come up with the answer. Okay?
Yes, sir.
Okay. With that, I'm finishing today. Thank you very much. One more question. Can I continue this 5 to 6 class every day? Or you have class this time?
I think that would work.
Sir, for MTech, you can,
Pardon?
for MTech student, this is fine, sir. But we'll discuss with our students and later.
Your voice is not, I don't know what happened. I'm not getting into. Can you repeat?
Sir, we'll discuss with all students and let you know.
Okay, okay. So then we will, if it's okay, we will see you all tomorrow at 5. Okay?
Okay, sir.
Okay. Thank you. Thank you, everyone.
Thank you, sir.
Thank you, sir.